Welcome back to the second part of our first day on the EuroK Symposium. I think we had a great start and focused a little bit on ATM in our first panel. Now we look into a wider perspective. We were discussing about already digitalization, virtualization at the first panel. Now we go a little bit more concrete into artificial intelligence. Very interested in this topic. I think we have high expectations on the technology. I just want to introduce the moderator of this session, Hassan Semde, who is an employee of EASA. He's a specialist in software and airborne electronic hardware at EASA. I hand over to you this panel, and very interested in your discussions. Good luck.
Thank you. Good morning, afternoon, everyone. Welcome to the panel 2 discussion regarding the automation and artificial intelligence. I will be the moderator for this session, and I'm really glad to be with you today to discuss such an interesting subject, automation and artificial intelligence. There will be a presentation for each of the panelists, followed by a Q&A session at the end of the session. And so feel free to ask your question along the flow of the presentation. We will be monitoring the slide view, and we will answer to your question at the end of the presentation. Before starting, I would like to, if you allow me, I would like to take a couple of minutes to introduce in detail all of our speakers and panelists for this webinar. Our first speaker will be Mr. Amar Menchouch, which is data processing and data science expert at Airbus Helicopter. Amar joined Airbus in 2013 as a research engineer. He first developed a big data solution which enabled the processing of the big amount of data collected from helicopters flying worldwide. He has been since contributing to the development of the helicopter data analytics activity in order to generate business value for Airbus and its customers. Previously, he has been awarded a PhD from the University of Rennes in 2009. He worked on the development of an AI-based system for medical image analysis. Before joining Airbus, he has been working first as a postdoc in the data science at the research department of the French mapping agency for 1 year, and a postdoc also at the LIPS at Aix-Marseille University for 1 year, and then as a software engineer at Thales for 2 years. Amar is also a co-author of more than 20 papers published in peer-reviewed conference journal, mainly in computer sciences and helicopter domain. Our second speaker will be Jeanette Beburn, Executive Vice President at Sea Ridge Technology. Jeanette is a technology leader with over 20 years of experiences, who has been at Sea Ridge Technology since the company early beginning then. As an executive vice president, she successfully contributes to maintain a consistent trajectory of growth for Sea Ridge with the focus of strategic partnership and complex deal negotiation. For more than a decade, now, Jeanette has served in the various leadership functions within Sea Ridge, including successfully leading multiple digital tower programs, designing effective corporate policy, and feeding into Sea Ridge innovation roadmap. Then our third speaker will be Dr. Darren Koffer, fellow at Collins Aerospace. His principal area of expertise is developing and applying the advanced analysis method and tool for verification and certification of high integrity systems. He is the principal investigator for Collins' team working on DARPA, Cyber Assured System Engineering, and Assured Autonomy programs. Dr. Koffer served on the RTCA committee SC 205, developing certification guidance for airborne software such as DO 178C. It was also one of the developers of the formal method supplement, the DO 333. He's currently a member of the SAA Committee G34, for artificial intelligence in aviation. Also member of the Aerospace Control and Guidance System Committee and a senior member of the IEEE. Our fourth speaker will be Wolfgang Astag, CEO of Atrix Advanced Traffic Solution. After finishing his military service in the German Air Force in 1990, Wolfgang was offered a pilot career at Dutch Lufthansa. After earning his pilot licenses in 1993, he decided to take up another challenge and graduate as a Master of Science in Computer Science in 1996. He then worked as a researcher in the University of Fribourg, in the Department of Artificial Intelligence, where he initially focused on multi-agent system and robotics. After becoming a world champion in robot saucer in 1988, he wrote a PhD thesis in airport surfaces traffic planning, in which he combined his passion for aviation and AI. As measured in TM system suppliers started to show great interest in his work. Wolfgang founded Atrix in 2002 with the clear vision to shape the ATM market by pioneering the development of AI-based technology for planning and optimization. So, and finally, our fifth and last speaker today will be Sylvie Schwader Perez. Sylvie has worked in ATM and aviation for more than 20 years now. She started her career consulting on the implementation of future ATM system. She joined industry leader Thales ATM in 2003, followed by the joint venture created by Thales and Airbus that established the César program back in this time. She was hired by Airbus in 2008 and worked with the SVP strategy to lead the creation and the subsidiary Airbus ProSky, where she was responsible for ATM services, including marketing, communication, and business development. She joined Inmarsat in 2015 and lead the IRIS project, developing satellite technology usage in dense continental areas. She managed the strategy and business perspective and is responsible for the relationship with the key industry and institutional stakeholder. That's it for the 5 speaker and presenter for today. If you allow me, just before deep diving in the presentation, I would like to recall the context of the webinar, which is organized around the emergence of artificial intelligence in aerospace industry. The aim of this session is thanks to some use cases that the presenter will introduce, to give you some example to discuss the implementation for AI future technology. We will discuss the technology innovation, the regulatory framework, and of course all the standardization which are currently ongoing. Last slide before the presentation. I wanted also to give you a very quick insight regarding the concept of automation and artificial intelligence. Automation and artificial intelligence are two distinct terms. Automation is the use of control system and information technology, reducing the need for the human input, typically for repetitive tasks. Artificial intelligence is the technology that appears to emulate the human performance, typically by using the learning. The point is that artificial intelligence is the key enabler for automation. in the presented slide, you can see a table extract from the EASA AI roadmap document that crystallize this concept with different level. The level 0 is no automation, so the human perform all the function. And the more you are going up into the level, the more you are increasing the automation. For information, the concept paper on first usable guidance for level 1 machine learning application was issued by EASA last week. So if you want to have more insight and more detail into this concept, I invite you to go directly on the website of EASA, and you can ask for more questions, and you can even make a review of the document that had been issued last week. Now I think that we can start with the presentation. Amar, if you're ready, the floor is yours.
Okay, thank you, Hassan. Hello, everyone. So today I will talk you about the use of machine learning to estimate the tail rotor power of helicopters, namely the H-175 helicopter. Let's start with a bit of context. In fact, the tail rotor power is data which can be used in different applications in the condition-based maintenance. Here, I make a focus on the maintenance credit because it is subject to certification, so it presents more challenges. As maybe you know, the design usage spectrum of helicopters assumes the usage that is as severe as expected in service. So the maintenance intervals are the same for all helicopters, whatever is their real usage. And the maintenance credit objective is somehow to adapt these intervals to the real usage of each helicopter to reduce the maintenance costs. And the data we collect from helicopters is a mean that allows to capture this real usage. However, sometimes important data are not registered on customer helicopters, and the tail rotor power is an example of such missing data. So the objective, the tail rotor power is only registered on prototype helicopters thanks to a specific and complex flight test installation, as we can see here in the middle, and which requires frequent adjustment, so it's not practical for customers to have it on their machines. And the objective here is to exploit the data coming from prototype helicopters to build a model that estimates the tail rotor power using a set of parameters that are also available on customer helicopters. Let's now go to the methodology. As I said, we use machine learning to estimate the tail rotor power here, because when it is applicable, machine learning allows to reduce development lead times, and also it allows a higher precision, for example, compared to classical analytical models. And the methodology itself is a classical one. So we start with a set of the flight test data. We do some transformation and cleaning on this data. For example, we remove outliers that do not make sense. We normalize some attributes and so on. Then this data is split in two data sets. The first one, the biggest one, is used to train, optimize, cross-validate one or several machine learning algorithms. And the second one is used to test the performance of the retained model on the data which didn't participate to its construction. Here, for example, for the tail rotor power on the top right side, we have the results. In green, we have the results provided by a machine learning model we built thanks to the gradient boosting algorithm. And as we can see, it's very close to the measurement, to the test data, which is in red. So it's very precise. And we have also in blue the results provided by an existing analytical model developed by engineers, which is also good, but less precise. As we can see, it often overestimates the reality. Anyway, once we have the machine learning model validated, then it can be deployed in production environment, or why not later deployed on board on helicopters. In this case, in our case, the model was deployed in production environment to process data, which comes new data coming from customer helicopters. So whenever we have a new data, a new flight coming from customer helicopters, we first check that we do not have any drift in the data. If no drift is detected, so we may be confident in the machine learning model we have, so the results are computed using this machine learning model. Otherwise, we need an alternative model, and here we use the analytical model as alternative model. The results then are stored in a database to be used in multiple applications. Just on the right side, we can see the results computed by the machine learning model, a distribution of the total power for two operators, an offshore operator and search and rescue operator. As we can see here, for the search and rescue operator, we have a certain time, a percentage of time spent in a higher values of the total power, which probably corresponds to the hovering operations the helicopters do. Now, let's speak about some challenges related to the use of machine learning in this domain. In fact, these challenges are part of those we can find in the EASA AI roadmap. And so during the development phase of machine learning model, in fact, we need to have data which is of a good quality. But in our case, we also need to have data which is representative of the reality, because we are trying to learn a model on a data coming from prototype helicopters, which is small data coming from few helicopters flown by one or two pilots in one or two locations. So, and then we intend to use this model on customer helicopters, customer data coming from multiple helicopters flying in different countries and performing different types of missions. So this is a big challenge for this kind of models. And I could say that this is the biggest challenge for these models. And when we deploy the model in production in the execution phase, we have also challenges. We have the classical one, the machine learning models. Most of them are somehow black box models, so we do not understand how they calculate the results. So we need them to be less black box models. But also, as I said, we may have drift in the data, and the models, the machine learning models, become not applicable. And in this case, we need to have alternative models, which is not something easy to have always. So this is also a challenge to consider in this case. And to finish, I wanted to mention an initiative, good initiative of the DEAL project, which is about dependable, certifiable, and explainable AI for critical systems, which addresses these kind of challenges. And recently, they have published a white paper, an excellent white paper, and I wanted to advise it to you because they make some proposals and they detail all of the challenges and potential solutions for this domain. Thank you.
Thank you, Amar, for this very interesting presentation. So next presentation will be a presentation from Jeanette with the focus on the level 2-3 use case and with some deep learning technology insight. So Jeanette, if you're ready, the floor is yours.
Thank you, Hassan. Thank you. And greetings from Ottawa to all the participants. It's truly a pleasure to be here and share these few moments with you and the community gathered here. I can't see my slides. Okay, thank you. There's a quote that I'm really fond of. It's from Jeff Hawkins. He said, sorry, it's going to be interesting to see how society deals with artificial intelligence, but it will definitely be cool. And this perspective has driven us at CRIC over the past couple of years. And we've seen that this also applies to safety critical industries such as aviation. So today, I want to share three things with you: why we decided to adopt AI in general and machine learning in particular, what we got out of it, and what we've learned along the way in the context of a deployment that we did in Heathrow, at the London Heathrow Airport. So to dive right in, since CRIC's early stages, we've treated data processing for automation purposes as a critical function. Having used traditional programming in general and pixels and comparison-based approaches in particular for years, we hit a sense of limitation to those methodologies. So we looked into the possibility of integrating AI from a higher level and machine learning more specifically into our portfolio of solutions, especially when designing applications for large hubs and high intensity runway operation airfields such as London Heathrow. And that's how our platform Amy was born. By adopting the model-based approach, we were mainly after three things: improved performance in the form of accuracy and confidence, increased processing capacity and speed, and resilience to noise. We've leveraged a multi-layered neural network to develop and deploy applications that range literally between stage 1 and 3 of the EASA classification. But I would like to list two of them here, one being the hold line surveillance system, which has been deployed at London Heathrow, and which is a wonderful decision-making assistant to the ATCO through the provision of an accurate real-time assessment of runway vacancies. And the second one being the traffic light surveillance application, which offers much more autonomy through its ability to integrate as many factors as desired in the decision-making process. One of the first positive outcomes of deep learning from a CRIC perspective and to our solution was the incredible amount of data that could be collected and processed. This leads directly to operational and business benefits for airports, which include better addressing issues such as tower in the cloud with a lot more confidence in the outputs, the possibility of recovering non-negligible portions of lost landing capacity in unfavorable visibility conditions. Next slide, please. Once we talk about what we did at London Heathrow and what we were after, I would like to talk a bit about the challenges that we've seen, not only with that deployment, but also over the years and still today, as with any innovation. The main one being, as the previous speaker mentioned, not only the quality of the data, but also safety assurance and regulatory approval. This challenge can be broken down from my perspective into three key elements. One being demonstrating a fail-safe operation to the regulator. Two being determining and convincing the regulator on how much data is enough. And three, making the black box a bit more transparent so that it could be understood how the decision-making process is structured. To get over those hurdles, CRIC chose to enter into collaboration agreements with certain regulators across the globe for the purpose of transparency and early engagement. So there was an element of mutual education and shared feedback, both from us as a technology provider and the regulator from an expectation point of view. EuroCAE Working Group 115 is a great step towards standardization with regards to AI in the aviation industry. And in line with that, and based on all the lessons we've learned over the past couple of years, we at CIRIJ recommend the verification approach development of the solutions, as it facilitates the anticipation of challenges at the operational readiness level by integrating that element of verification early enough in the projects. It's easier to, one, engage the regulator, two, foresee where the roadblocks will appear, and three, be able to design validation methodologies that are compelling for both the users and the regulators. A detailed, thorough safety assessment will always reveal the adequacy between the proposed solution and the business environment and objectives. So almost a decade after kicking off the AI experience at CIRIJ, the question could be asked, what have we learned? Well, for one, we've learned that data is not just data. Every data set is not equal to the next, even sometimes when the source is the same. Quality and quantity are key, especially in I don't want to say non-regulated environment, but in a context where regulation is still in, standards and regulations are still being developed. Pre-processing and annotation are buzzwords in our vocabulary, and they bring their fair share of challenges as well. Given that we learn as the models learn, we also learn how to adapt to the challenges and the difficulties of cleaning up data sets and making them fit for purpose. One aspect that I want to highlight is the technology business case adequacy. We've tried a lot of applications over the past couple of years, and I feel this is strongly required to ensure an increased fitness for purpose. AI is not always the solution, and I can't believe I'm saying this out loud, but it's true. Although the technology knows no limits if we're talking about the type and the quantity of data that can be processed, and despite all the excitement about achievable performance, we have examples of deployments with low value return from a business and operational point of view. Given the time that I have remaining, I will not go into details listing examples. Rather, I want to emphasize the necessity to assess not only the feasibility of a project when using machine learning and deep learning specifically, but also the applicability of the envisaged solution to the market and target operations. Before I hand back to Hassan, I would like to share our vision for the future, which is a smart airport in a smart city with door-to-door connectivity. Just like smartphones are making our lives easier today, smart airports, and this is our conviction at CIRIJ, will make traveling funnier and safer for everybody. Thank you very much for your attention.
Thank you, Jeanette, for the presentation. Our next speaker will be Darren with a presentation focused on the assurance processes. So Darren, if you're ready, the floor is yours.
Great. Thank you, Hassan. And thanks, Jeanette. I think you've provided a good intro and raised some of the concerns that we have from an assurance standpoint, looking at deployment of AI and machine learning components in particular. The talk fire aim with the idea it's like we've gotten things out of ready aim fire. We are needed to deploy systems for which we don't necessarily have the assurance evidence that if we go to the next and we can see this even more other especially automotive, for example. We have a great body of theorem and theory and new computing power available to us that's provided advantages. And we've proceeded to deploy those and show impressive capabilities delivered in real and safety critical in automotive, for example. If we go to the next slide. There we go. I think before letting our enthusiasm get out of hand, it must be tempered by the need for assurance evidence. And so some of the work that I'm involved with now is looking at how do we provide the assurance evidence that we need for safety critical applications so we can get things in the right order. Next, please. So this is the assurance process with the document names from the North American point of view. But the things are fine in the top half of this flow when we look at the means of compliance with the safety assurance and system development standards. But when we get down into design assurance, that's where things start to get more complicated. And the processes and guidance that we have in place now is not at all it's not well suited for AI and machine learning applications. So let's say a bit more about that next, please. Specifically looking at DIA 178C or ED12 for this. We're showing the next slide. There we go. The purpose of 178C, of course, is to demonstrate the software implements its requirements, but importantly, that it does nothing else, that there should be no surprises. So it assumes this more or less waterfall development process where we refine system requirements to high-level requirements to low-level requirements and produce source code and executables. And the primary assurance means, or probably is the development of requirements-based test cases to show that the final product implements the requirements that have been levied upon it. And the problem is that our traditional assurance methods are really not a good fit. The complexity and the design intent reside in the data for machine learning and data-driven applications, not in the code that's produced. So when we do things like structural coverage metrics, they don't provide the same insights to the system. So in fact, one of the important things when we're doing requirements-based testing is to know when you've done enough testing. And our structural coverage metrics are the primary mechanism for doing that. And for example, for deep neural network systems, you can generally achieve 100% coverage with a single test case because there are not decisions and embedded in the source code itself. So we don't learn about, from our structural coverage, we don't learn about whether there are missing requirements, whether our testing is adequate, whether we have dead or deactivated code, and importantly, whether there is any unintended functionality in the system itself that could result in surprises during operation. So one of our main challenges is to determine how we can measure the completeness of our requirements and verification results to ensure the absence of unintended functionality. So we've been in several different programs trying to answer this question and determine how we can provide the assurance evidence that we need for machine learning systems in a different way from how we do it from traditional systems. So go to the next slide, please. And I'll talk about an example that we've been using in the DARPA Assured Autonomy program in collaboration with a number of universities and our colleagues at Boeing. We're looking at this autonomous taxiing demonstrations. a camera-based system. It's deployed on this Cessna Caravan with both a real aircraft and a simulation environment for development and testing. And the objective of the machine learning part of the system is to, based on forward-looking cameras on the aircraft, as the aircraft is doing, surface movement, driving on taxiways and runways, to determine where it is relative to the center of the runway or taxiway, to provide guidance information to steer the aircraft and make sure it stays close to the center line and away from the edges. So this estimate of the cross-track error is fed to a simple yaw controller, the rest of the aircraft control. And the point is both to ensure that the aircraft, this cross-track error measurement is correct, and to determine, to avoid any unnecessary stopping on the runway, because that's also a safety issue. So we've deployed in this system a number of different technologies to try to either eliminate, bound, or detect unexpected behaviors in the system. So one of the main things that we're doing is the use of runtime assurance, or the use of a simplex architecture to bound the autonomy. And the idea there is that you independently, using high assurance components, monitor either the safety state of the system, or the inputs to the learning part of the system, or its outputs, or the internal state of possibly of the learning system, to determine whether it's operating correctly or not, and whether it's violating the safety of the system. And if so, intervene and switch over to an alternate source of control that is known to be safe, although possibly providing less performance. So in this case, we have a combination of diverse monitors based on the GPS system, the inertial sensors, and some traditional computer vision algorithms to detect lines and markings on the taxiway. And these will intervene to either allow the aircraft to proceed under control of the neural network, or to slow it down and perhaps at least reduce the stopping distance and increase the safety margins, or to stop the aircraft altogether if it's in an unsafe state. Other technologies that we monitor inputs to the neural network to detect anomalous, those that deviate or out of distribution relative to the training data that was used to create the neural network itself. Really new and gradient-based methods that and identify when have deviated from what the neural network has come to identify. We can't trust it. We have members of our group who are developing using neural network or formal methods based on SMT mining techniques to be able to provide a complete assessment of the neural network and evaluate its robustness characteristics. And then we have other members of our research team who are looking at new test generation and coverage metrics based on manifolds, the embedded manifold in the internal representation space of the neural network itself, to try to provide meaningful coverage metrics that apply to neural networks and can give us the same sorts of assurance that we would have for traditional code. So there's a number of really interesting research activities that are hoping to address this need for high quality assurance evidence for the use of machine learning technologies in safety critical applications. Next slide. So finally, we hope hopefully through all this work, we can get things back in the right order. These are the sorts of technologies that we're looking at in the Working Group 114, AI and Aviation. This is also drawing on the ASTM F3269 standard for runtime assurance architectures. And we're interested in looking at some more information on this particular example on the runtime assurance applied to the aircraft taxiing problem. There's the reference from last year's DASC conference. So that's it. Thank you very much.
Thank you, Darren. Thank you, Darren, for this very, very interesting presentation. Our next speaker will be Wolfgang, that will be giving some insights regarding the AI involved in decision making toward autonomy. So Wolfgang, if you're ready, the floor is yours. We can't hear you, Wolfgang. Maybe you're still on mute. Maybe with your microphone settings.
Can you hear me now?
Yes.
Okay, I'm sorry. Yeah, thanks for giving me the chance to demonstrate and explain, give an insight of what we're doing at Adequacy and Frequentis in the field of AI. And as you may be able to see on my first slide, we're changing the topic here to the operational context of aerodrome control. And in that case, we have aircraft and vehicles on the ground and on the approach or departure, and we've got the controller. And what we have is a lot of equipment on the surveillance side, like radar and MLAT, ADS-B, or video cameras, which is enhancing the situational awareness of the controller. And on the right-hand side, we have certain equipment to provide guidance to the pilot by radio communication, by switching lights, or by sending data link messages. And as this illustration indicates, we've got a loop, but this loop is what you call a human. It's an open loop. So we've got everything has to go to the human brain, and it's very difficult to automate certain aspects of this entire operational context. And we call it also the human on the loop. And so the first step we have to do is to enhance this loop, to have an automation system, in which case our product is called TowerPad, has access to the same sensoric elements and has access to the same, let's say, actuators like lighting systems, stop bars, center line lights, or data link messages. And now, as this picture clearly shows, now we've got a real loop, which is even closed, but it's driven from inside. So this means now the controller can actually delegate tasks to the system and then focus on monitoring the execution of the delegated task, basically. And here now, this is where AI comes into the game, because now we're talking about automation, and AI, I think we all know, is not a very new thing. I mean, it's since 1950s. We're using AI in our car navigation systems for route planning and stuff like that. But I mean, thanks to the help of this massive amount of data in Google and Facebook, it has a certain became a certain hype, which is good. And what we clearly distinguish now, how can we use automation and AI in particular to support this control loop and to shift to more, let's say, intervention by exception principle instead of an ad hoc control concept. And before I go into that detail, I would like to remind us that we have two types of AI. So the one type is called model-free AI, or data-driven AI, and the other one is the model-based AI. And as Jeanette already just gave some examples, is processing video images, for example, is a good example where you can learn from a large amount of historic data and come up with an approximation of what you want to achieve. Is this a penguin, an aircraft, or whatsoever? But it's just an approximation, because model-free means it has to learn its kind of function to distinguish or to analyze from the data. Whereas in contrast, model-based, you have the know-how built in already. You tell the system what the domain is, what the rules are. It does not have to be derived from sample data. And so this is why, let's say, model-based AI is much easier to prove the correctness of these kind of algorithms. And this is what you see on this slide, where basically we see, as Atrix and Frequentis, three different areas of AI. So the one is the surveillance data processing. And like Jeanette and others, this is where we have a lot of data we can learn. We can detect objects, relevant objects, even while they are static or kind of partially occluded. We can detect events, something has passed a certain threshold or entered an area. And the main reason on the left-hand side why we should do so is basically to further enhance situational awareness of the controllers. But also, I mean, to have a safety net, because the controller can't have it, or he or her can't have the eyes everywhere. So AI is a very good idea, but it still requires a human verification process. Is this actually really happening, or is this just a kind of false positive? On the right-hand side, you see on the microphone, the headset, another AI. There's speech recognition. For example, you just listen to what the controller says, and based on that, you detect the clearance, which was given by RT, and then you can trigger certain actions like switching stop bars or providing an alert, for example. So that's also a very good example where we're active in right now to see what can we do with speech recognition. So both on the image processing on the left-hand side, but also on the right-hand side with speech processing. But let's say one of our main focuses is the one in the middle, which is the model-based AI, because now we really talk about decision-making. The other ones are more or less decision support or information analysis. But what we do here is really the decision-making. And there are a couple of examples like, let's say, sequencing of aircraft, the optimum departure sequence, or if you have converging traffic at an intersection, you know which one has to give right of way to the other one. But also routing, as I said, which is the best way to avoid conflicts, to have a kind of time-efficient route. So planning and routing is another very important example. And these are examples you can't learn from big data because just to get an idea, if you have a complex aerodrome, you have multiple thousands of route combinations. And if there's just one closure for, let's say, runway refurbishment or taxiway refurbishment, you know, there's no reference data. You don't know what to do because you have not, the situation was not there. So this is where we think the model-free methods reach their limits or are not applicable anymore. So this is where model-based processes are quite important. And but whatever road you take, so most important basically is AI or automation can go wrong, and we need a guard. So we call this an AI containment component. That means whatever AI has detected, like a clearance from the controller by speech recognition or a certain event from the video system, whenever there's an action behind that, like switching a stop bar on or off, that has to be assured that it really is safe to do so. And so apart from just, you know, trying to come up with these AI components, one of the other key elements is really to have this kind of containment component to make sure it doesn't go wrong. And so, and this has to go in parallel. I mean, it's good to go ahead with one or the other, but they have to be kept in sync. And what I'd like also to mention is, because EASA is primarily looking at data-driven or model-free AI, but they're also looking at hybrid AI. And that might be another good example, because for speech recognition, I mean, there are not millions of options. You wouldn't expect a fairy tale. You would expect a landing clearance. And so what our containment model can do, it can share the operational context. So there might be a British Airways on the final approach, and we may expect a landing clearance next. So this kind of contextual information, which comes from a model, helps AI to come up with the right detection, because the probability of what has been detected is higher if you narrow down the search space or the possibility space for model AI. And this concludes then my contribution to say these three elements on AI plus the containment ones are the ones that we are currently focusing on. And some of these components are in operational use since 10, 12 years already. And we expect, let's say, some very high developed, even autonomous components to be deployed within the next 5 years. Thank you very much.
Thank you very much, Wolfgang. Our next speaker will be Sylvie. So Sylvie, if you are ready, the floor is yours.
Thank you, Hassan. Good afternoon, everyone. I'm very happy to be on this panel. I will not present a pure AI use case. I will rather mention a technology which is an enabler to AI and automation, which is around data provision. I think that I will be very quick on the introduction, because the need for digital transformation of aviation and air traffic management And the need for automation and artificial intelligence has already been presented by many speakers before me. I will just recall one thing. So AI and automation, they rely on data communication, and the air-ground communication today cannot really be called as fully digitalized. It's all a lot relying on the voice and the VHF data link for air-to-ground interactions between the pilot and the controllers, but also between the aircraft systems and the ground systems. I think that Mr. Hololide used even the word archaic protocols, and he also mentioned the very limited capability to exchange meaningful data. So in this context, the European Space Agency launched the IRIS project to support the CESAR GU to develop a digital communication service based on satellites. It created a partnership with Inmarsat, it's still in place, with the rationale to adapt the existing Inmarsat infrastructure for continental airspace. Today, our systems are mainly used in the oceanic and remote areas. So the partnership was really to address the limitation of the existing communication infrastructure in the continental busy airspace, like European airspace, and really think to enable the advanced air traffic and airlines operation services that will use automation and artificial intelligence. The idea is also to have a global service with a connected cockpit everywhere. So aviation doesn't think regional, they always think global. This is why this partnership was established, with a view to provide a service, not to deploy a big infrastructure on the ground, but to use the power of satellites that can cover very large areas. Our service are done with 3 satellites to cover the entire globe. The target being to have an entry into service by Q1 2023, so it's nearly tomorrow. So what does this technology or service brings? So as you can see on this diagram, of course, bandwidth, first of all. Although you cannot compare the bandwidth we are providing over this safety L-band, well, this band of frequency is reserved for aviation. It cannot compare to the broadband services that are provided, for example, in the cabin of the aircraft. Still, it provides large enough capacity to address the new air traffic management and airlines operation needs. It's an IP-based communication network. It has global footprint, and service availability will be Europe first, but global service can be provided in the coming years. Another very important dimension is cybersecurity, because especially for AI, you have to have trust in using a technology. And this is an element we have been developing within this project. The technology is mature because it's actually not a new technology, because it's already being used as I mentioned, by nearly all the long-range aircraft flying over the oceans and remote areas. So it is just, let's say, an adaptation of the existing service to meet the continental airspace requirements, in particular for the performance targets that are established by ICAO. And what it brings also is new lighter terminals adapted to the narrow body aircraft, because when we talk busy continental area, we talk about the narrow body fleet, not the long range aircraft. And of course, it's service-based. As I briefly mentioned before, you don't need any complex infrastructure on the ground to deliver the service to the air navigation service providers. And very briefly, just to come back to the application and rather connect to the topic of today's, the use of live data so during the flight will support, for example, a very pillar project of CESAR, which is the 4D trajectories. And we all know in the aviation business that more precise prediction of the flight trajectories will increase the conflict resolution that will be supported by AI algorithm and automation. Also, to mention that unmanned air traffic is also one of the applications that the IBIS service will support, and we have already made some demonstration of the use of the SATCOM service for the command and control link for air passes. And just to recall one of the remarks from Mr. Hololai at the very beginning. So, of course, ATM is facing a big challenge today, and there is a big crisis still. Even if the sense of urgency has decreased, innovation is still needed and has to continue. And this technology is nearly there. 2 years' time, it's tomorrow. So it's really a quick win to deliver some of the key benefits of improving ATM, which will lead to 5 to 10% of CO2 emissions less. So that's the end of my presentation. Thank you very much.
Thank you, Sylvie, for this presentation. So it was the last presentation for today for this webinar. So I propose to go directly to the Q&A session. I have one question regarding the verification of the AI ML application. Maybe Darren, if you can you, I will try to, just 1 second. What is your position on the use of formal method for the verification of AI ML application? Because there is a lot of question regarding the verification of AI. What is your position regarding what is currently done actually today regarding that? I think you are in mute, Darren.
Just drop.
Just drop. Okay. So maybe we are going to take another question, or if somebody else wants to respond to that.
Yeah, sure. As I said, this kind of model, free AI, is very difficult to verify. Depends on the data and whatever, and the conditions may change, different lighting conditions for video processing or stuff. We have reflections caused by rain. So it's really difficult. And if you look at COVID, there was also another question regarding flight tracks and try to learn from flight tracks, of past flight tracks. When we do the recovery of COVID, we will see patterns we haven't seen before. I mean, even if you're trained in AI with the data of the last 10 years, the traffic patterns will change, and like the city pairs will change and stuff like that. You have new aircraft types and less A380 flying. So this is where AI might be really limited if you are encountering the unexpected. If you really have very repetitive tasks, like, I don't know, face recognition for borders and stuff like that, I think this is really helpful, but that's not safety critical. And because of this lack of verification possibility, this is why we focus on this separate, let's say, guard function, or this kind of AI containment. It's good to verify that AI works somehow, but you shouldn't even trust that. So have a separate box around the AI to contain it and to make sure it doesn't harm the operations. So this is the approach we take.
Yes, I completely follow you on that. And this is also mainly the concept of the trustworthiness AI approach that we have at EASA, with the different building blocks that all together help to have AI trustworthy, let's say that. I have another question regarding the maintenance aspect, maybe for Amar. How the so-called machine learning black box model can match with the maintenance approval requirements of the Airworthiness Authority. So I believe that you already started with some insights regarding the potential mean of compliance with for the maintenance.
Yes. This is I don't know if I could have a complete answer today on this question. The maintenance, I would say, when you have machine learning, you need something we do not have. We need to detect what we call the drift of the data. And today, the drift of the data, we do not have a sophisticated means to detect them. So once we have a model which is running in production, if new data is coming from in our case, customer helicopters, if the model, the drift is detected, so the model needs to be learned again. So the idea is to learn the model from time to time. This is the choice we made in our case. We do not have continuous learning. Once we have detected a drift in the data, so we need to learn the model again. So we learn it and we deploy it again. But all these questions, I think we do not have all the answers today.
Okay, and just to add to what you just said, I will go again on the different building blocks that you presented in your slide. The EASA approach with the trustworthiness, let's say, certification. There is 4 building blocks, and the one with the trustworthiness analysis, the block for the learning assurance, and the one for the explainability, and there is also the block for the safety risk mitigation, in case there is no possibility to open, let's say, the black box in certain conditions. So there is also, let's say, a way to cope with certain solution if it's not possible to really get deeper in opening the black boxes.
But this is just the issue because we do not have always alternatives to the model we deploy. Once we have an alternative, yes, we can. In our case, as I mentioned, we have 2 models. One that it looks like a model-based inference, and another one machine learning-based inference. And it's not always for all problems to have 2 models. Often we have machine learning model which can be built, but it's not always easy to have an alternative model. So
thank you for your comments. Maybe one question, one question to Jeanette regarding the future of AI. How do you describe the way ahead for the next 5 years? What needs to be done concretely today to get closer to the full deployment of AI? What is your idea and your insight regarding to that? You are in mute.
Can you hear me?
Yes.
Okay. If you're talking about full deployment, with the definition of fully operational, non-overridable applications, I think what needs to be done is go on full speed from a regulation point of view, a higher and earlier engagement of regulator, putting the focus on performance-based evaluation. And the reason I'm saying this is because there is this concept of linear development where we need to start, like it will require a level 1 development, solutions development, then 2, then 3. I think business needs, the size of the environment, business environment, context will dictate which level of development will happen, and that needs to be accommodated in the evaluation approach. So I think another key thing would be to strengthen the existing ecosystems, at least from a data storage transmission point of view, infrastructure upgrade point of view, integration and interoperability as opposed to simple compatibility or de facto standards. And I must say that a lot is being done. So my personal conviction is that future is nearer than we think.
Thank you very much for your answer. Maybe one last question to Sylvie. What is your view with the potential? Because I know that in your presentation you present also some data as a topic regarding the SATCOM. What is your view with the potential limitation of the SATCOM, potentially the bandwidth for AI and ML application?
Well, today we have made some capacity simulations, and it's strange to think that even today the data link is very slightly used in Europe. There's only two messages that are digital exchanges between the cockpit and the air traffic controllers per flight hour or per flight sector. So it's really already minimal. So we made some simulation to consider not only the current use, but the use for 4D trajectories, and also the use for airlines operational communications. Not and shows that we don't have any limitation of the because of the capacity of the systems, and we have even 100% of margin. So we are now entering into future simulation, assessing what if we want to support additional services to the airlines. It doesn't seem to be that the capacity will be the issue, especially that in Europe we have planned that there's not one technology that will be used by the aircraft. We have what we call the multi-link concept, which is planning for several technologies, communication technologies, to be combined and to be used during the flight by the aircraft and the controllers.
Okay, thank you. Thank you very much for your answer. I think we are already, that's already the end of our webinar. Thank you again to all the panelists and to the participants for your presentation, and thank you for all the viewers for all the questions. I have no doubt that the artificial intelligence and aviation are together a bright future. So thank you again to watching us. Thank you.
Thanks.
Thank you.
Thank you.
Okay, thank you very much. That closes our day one. Quite interesting. Quite difficult to summarize what we did today. I mean, we started quite nicely with, and Sylvie quoted Henrik a couple of times today already. I think he gave a good perspective from a, I would say, the political dimension of the expectations in aviation. I think that was a nice setting the scene for day one, while we concentrated on day one already. A lot of innovation, technology, and I'm really inspired. I mean, panel one was mentioning, and I have to look into my notes, but yes, out of the wise persons group, the airspace architecture study, we as EUROCAE went finally into a standard developing process already. Are we too quick? Are we too late? Henrik made a statement that we have to be much quicker in that. So I think we are good on time here. We have seen how crucial, and we have heard how crucial it is, harmonization, interoperability. Those are keywords and buzzwords, especially for us as a standardization organization we take with us. What I also learned in panel one was the confetti airspace. I didn't know that a confetti airspace exists. So that's something I have to take with me, but I learned this is something very typical, very special in Switzerland. Machine learning, artificial intelligence, Hassan, you did a good job in moderating that. And I think it was a wide perspective in different applications, from using learning, the helicopter learning about tail rotor power, how much tail rotor power is needed, deep learning on sea-rich application, and how much data is enough data, you know, how much data you need in order to have a machine learning and deep learning application. So assurance level that Darren brought us to this point, and also explained what we need in order to have this assurance when we implement that, and the AI containment. So what does it mean if we have AI applications and we need to contain that in a way in order to have some safeguards around that? Sylvie then brought it up to the space and made the link to space. But I also liked, she also made the link between AI and cybersecurity. And again, she brought back from panel one the service-based architecture and the service-based infrastructure. Also, Jeanette mentioned nicely that the regulation is needed in a more performance-based way. I think, Hassan, we know that at the EASA level, this is EASA is quite good in that and enhanced in that, especially in new developments, in new technologies, in newcomers, in what we have in our airspace. We see that a lot more performance-based regulations, but we also know that we have to work closer together in order to complement this performance-based regulation with more standards, with more guidance material, with acceptable means of compliance at the end of the day. And Jeanette also said, the future is nearer as we think. So promising words for that. With this, I want to close day one and want to thank the panels we had so far, panel 1 and panel 2, all the speakers, all the participants online who were able to join us today. So thank you very much for that. Again, our sponsors, it would not be possible to have a symposium like that without sponsors. So thank you very much to our Silver and Pro sponsors for that. And just before I leave you for the evening or the morning, wherever you are, just a quick introduction where we are going tomorrow. And I think we have the introduction for tomorrow. Day 2 will start at 12 o'clock, right? Oh, it's coming soon. Okay. Okay, day 2 will start tomorrow at 12 o'clock with a visionary talk. So from a more organizational or institutional perspective, we will discuss the vision and the strategy we have in aviation, having guests from the European Commission, from ICAO, from IATA, and from EASA discussing on those topics. Please be aware, there is the opening statements are pre-recorded, are available on our website. Please go there and listen to that. It's really, really interesting. Very well invested 20 minutes in listening to this opening statements of our guests tomorrow. And excuse me. And this visionary talk will immediately go into panel 3, where innovations, environment, sustainability will be discussed on an aircraft level. So that will give us more insight then on the solution the industry has already today. So really good program for tomorrow. Thank you very much on that, and have a nice evening and see you all tomorrow. Thank you.